Jnanam Paramam Dheyam. Knowledge is supreme.
Hello and welcome back. Power devices are the power switches which we have considered or we have talked about when we first introduced the switching matrix to represent a power electronic circuit. We will start with power diode. The reason is that power diode is probably the most basic device out of all the power devices, and if you understand the power diode, then it becomes easy to understand other more complicated power devices. Now, one of the things that differentiate between what are called the power devices and the low power signal level devices such as the diodes and transistors, is the power level. So, here in power devices we are talking about very high power levels. Talking about power devices in general in the power electronic circuits, we assume all the ideal properties of the power device. For example, we assume large breakdown voltage, we assume fast turn on and turn off times, we talk about the low drop voltage drops and resistances across the device when it is conducting, and we also talk about a capability to dissipate a large power by these devices. You will see that in due course when we do some analysis that these properties, they are actually having some sort of a trade off between each other. So, basically there is no single device which will have all the properties, and therefore a person who is actually designing a power electronic systems and is trying to use power devices, he will have to use what is the best available device with all the best possible features. He will not get all the features, and at the same time he may have therefore more than one choice. So, it may not be a very unique device that he can use, but he can probably choose from a given set of devices. Therefore, it is important that a design engineer, he understands what exactly is the working principle of the power devices. What would be the meaning of a certain trade off? Suppose a design engineer decides to compromise on the losses, in favor of getting high breakdown voltages, then what is the price he will have to pay for that and how he will actually compensate in his design. So, all these things actually demand, or in other words I should say that a good and optimum design, it demands that we know the working of various power devices, and power diode, it actually serves as a very good precursor to such a study. So, now let us just try to see what is the structure of a power diode, and let us try to see how it is different from a low power signal level diode, or we will just call them as signal diodes now. So, what you see right now is the structure of a power diode. The symbol of the power diode is also given on the right side. So, what you can see that just like the signal diodes, you again see that there are two layers. One of them is P, the other is N. So, there are two P and N type materials which have been brought together, but now you also see a third layer which is sandwiched between the regular P and N layers, and this is actually a lightly doped N layer that you see. Now, the doping levels are actually, you can see in this slide, these are the typical highly doped and lightly doped concentrations which are given. So, we begin by an N type substrate which is heavily doped with something like 10 raised to power 19 atoms, donor atoms per centimeter cube, on which is grown an epitaxial layer of a lightly doped N material. So, basically you have a much reduced concentration in this region of the donor atoms, it is only 10 raised to power 14 atoms per centimeter cube. Over this is grown a highly doped P layer. So, again if you see the concentration, it is 10 to the power 19 atoms, acceptor atoms this time per unit, per centimeter cube. And this P layer is connected to the anode, which is serving as the anode of the device through a metallic contact, and at the bottom you can see that there is a metallic contact which is providing cathode connection to this device. The symbol of this diode is same as the low power level diode, there is no difference. But I would like to mention 2 or 3 important differences between the signal diodes and the power diode that you can see on your slide right now. One of them is in their IV characteristics. So, one of the things that you will see is that if I draw the IV characteristic of the 2 diodes, and let us say I use a green pen to draw the IV characteristic of a signal diode. So, you can see that it actually is going to rise exponentially later on, and there is what is called a cut-in potential or contact potential, and the device actually starts conducting only after that. What you will find in the power diode, however, when you actually try to measure its characteristics I versus V, you will find that first of all the value of this cut-in potential is going to be 1 or 1.5 volts. So, this is going to be more. Let us say I just kind of magnify and show you. So, the characteristic would be something like this. Okay, so what you see in this in this drawing is that the red color characteristic of the power diode is more linear. Now, this linearity is coming because you have an N minus layer in this device, which actually is obviously having much less charge carriers and therefore contributes to more voltage drops, ohmic drops, which actually brings in this resistance type characteristic. So, that is why you see instead of an exponential in the green one, you see this linear curve in or linear plot in case of the power diode. While looking at the IV characteristics of the diodes, it is important to note that even though the cut-in potential or the threshold potential or the contact potential of the device may be given by a standard constant value as we discussed in lecture 8, the actual voltage drop across the device may be higher, something like 1.5 volts or even 2 volts due to the ohmic property of the device. Hence, it is important that we do not confuse the cut-in potential or the contact potential values with the actual voltage drop across the device. The other difference between the two is, of course, the major difference, as you already would have noticed, that you have only P and N layer in a single diode, while you have 3 layers. You have a lightly doped N layer which is sandwiched between highly doped N and highly doped P layers. So, that is of course another difference. The third difference point is that the doping levels in power diodes, they are higher both for P and N type, they are higher than what you observe in case of signal diodes. So, these are some of the the differences between the 2 types of diodes. Now why there is a need for N minus layer? Let us just study this part a little bit. Now, we have seen the forward bias and the reverse bias operation of the diode earlier, and in principle it remains the same. The physics of the power diode operation remains the same both in forward bias and in the reverse bias. So, there is no difference between a power diode working principle. However, let us see what happens because of the presence of this slightly doped N layer in between the P and the N layer, the main P and the N layers. So, in the last lecture, that is lecture 8, we had obtained an expression for the breakdown voltage VBD, which was given by, if I remember correctly, by equation 21. So, you may refer to your lecture 8 for this equation. Now, assuming, let us say that we consider a special case now where we say that the P side of the PN junction is more heavily doped compared to the N side. Okay. Now, which actually means that NA is much larger than ND. We can show that VBD will turn out to be some constant divided by ND. Let us call this as an equation star. Now, similarly, if we use equations 10, 11 and 13 from lecture 8, okay, and if we use the star equation that we just obtained, okay, we can also show very easily that the width of the drift region actually is about, you can show approximately K2 times VBD, okay, where K2 is basically a constant which will come by substituting the numerical values to the various variables which are there in the equation. Okay. Now, let us call this as equation double star. Now, what are the conclusions that we can draw from these two equations, star and double star? Okay, so, one of them is a very important observation that shows that if we need a large voltage breakdown capability, so large VBD if we need, okay, it means that the density of the donor atoms must be as small as possible as per the equation star, okay, which means that we are saying that we need our N layer to be lightly doped. And the second observation we can say is that a large VBD will also require a large width of the depletion layer, okay. So, which means that my W drift should be large if we want to have a large VBD. Basically, this means that while I will apply a large voltage, okay, across my PN junction, then my drift layer should be able to absorb the entire the depletion layer. So, this is the major thing about the power diode. Basically, the idea of using this N minus layer is to provide a high reverse voltage capability to this device, and this you will see would be very apparent when we use applications such as rectifiers, where you actually have large reverse voltages coming across these devices. So, you will see this happening even in the case of SCRs, the silicon controlled rectifiers, and you will see that they also need a large negative voltage capability because of this. The other devices that we will study in due course, such as the MOSFETs, the IGBTs and the power BJTs, they lack this particular feature. They lack this capability of being able to withstand a large reverse voltage across them, and we will find that because of this reason, their application in processes like rectification is going to be limited. Okay. Now, the question is that if power diode is able to withstand a large negative voltage, reverse voltage across it, okay, then, and we are achieving it by actually inserting a lightly doped semiconductor layer, N minus layer in it, then obviously you are having a region which is not having sufficient charge carriers. So, if I draw this situation, let me say that this is the diode, and let us just divide it into 3 regions, P plus, N plus and in between N minus, and now you have let me just use this blue pen now, and now let us say we have the charge injection which is taking place. So, let us say we are trying to study the diode now during the forward conduction, okay, when it is conducting in the forward biased case. That is the time when the current flows, and that is the time when you expect the drops would take place. What happens? If we just go by what we have seen so far without applying any other explanation, we will find that it turns out to be a device with a huge ohmic drop, a very big ohmic drop, and probably the device would be impractical for use. But a very good thing that happens in bipolar devices such as the power diode or the power bipolar junction transistor and even the insulated gate bipolar transistor that we will see later is what is called conductivity modulation. Okay? So, when you have your diode which is actually connected in the forward bias. So, you can see the polarity of the external voltage source that is applied. Okay. Now, what will happen that holes will be injected from P region to N region during the forward bias. Okay. Now, because N region is not having enough electrons, definitely not as many as the corresponding holes in the P region, because that is highly doped. If the injection of holes from P region to N region or N minus region is large, your electrons in the N minus region will not be able to neutralize the holes. Okay. And therefore, there would be an actual accumulation, okay, at least temporarily, of net plus space charge in this region, in the N minus region. Now, the moment there is a net space charge which is positive in this N minus region, you have electrons, which actually start jumping and going into this N minus region. They all cross over. So, what happens basically is the net result of all this is that this particular region, which was actually devoid of charge carriers, because of which we were actually afraid and anticipating that there would be a big ohmic drop, actually has become rich in the charge carriers. Now, this phenomenon of injecting the holes from the P type to the N minus layer and injecting electrons from the N layer to the N minus layer, we call this the phenomenon of double injection, and it actually leads to increase in the conductivity, which is also called conductivity modulation. We will find that this is going to be the case with all the bipolar devices. In fact, all the bipolar devices will have this phenomenon, and therefore, they are usually having much less on time losses are much less in bipolar devices. Okay, let us try to see that what exactly are the properties of diodes when it is used in power electronic circuits, because you know that the power electronic circuits require this power diode to actually go on and off. So, this is going to be working as a switch, an uncontrolled switch in a power electronic circuit. So, it is important that we see the switching characteristics of a power diode when it is actually used in a power electronic circuit. So, what I have done is that on this sheet I have just drawn the typical switching waveforms for the voltage and the current across a power diode. So, what we are doing is we are looking at both the turn on and turn off switchings of the diode. So, what you see on this side, on the left side, okay, if I just draw this, on the left side is a turn on and on the right side is the turn off switching of the diode. During the turn on, let us say that the reverse voltage across the diode, just when we started to turn on the device, just before that, it was, let us say, minus VR, and the current was obviously 0. So, the current starts rising from 0, okay, and this is what this line shows here. It goes up with a slope which is defined as dIf by dt and would be actually determined by the external circuit elements which are there, like the inductance. Okay. This could be the legitimate inductance or it could be the stray inductance that might be present in the circuit. Now, at the same time, during this upslope of the current, you have the excess carriers which are all getting accumulated in the lightly doped N minus layer. Now, what is happening to the voltage across the diode at that time? The voltage is also rising. Okay, it is rising starting from minus VR and it is going up. Now, ordinarily we would have assumed that it would just go and get settled at at some value here, which is the forward voltage drop. But there are a few issues. One of them is that during this time, which I have marked as T1, during which the current through the diode is building up, the excess charge carriers have still not built up completely. So, still there is a high resistance across the N minus layer or the drift layer of the device. So, that is one thing. Secondly, there are stray inductances on account of the silicon wafer as well as the leads. So, this voltage what you see, it actually tends to overshoot, and it actually, you can see that I have marked this as Vp, it actually reaches a value which is Vp. Now what happens at the interval after T1? So let us mark this as T2. Okay. Now what happens during T2 is that my current the diode current has settled. Okay. It has settled to a constant value here. So let us say this is the constant value IF. The excess carriers have now all built up. So the losses or the voltage drops across the n minus layer have also reduced drastically. Okay. And they have actually, because of the conductivity modulation that we have seen before, you have very low drops there. And that is the reason you find that the voltage across the diode, it falls quickly from its value of Vp and it comes to its on state value, which is its regular normal, this it actually comes to the V on value. Now this is where it continues as long as the diode is conducting the forward current IF, which is shown here. Now let us consider the turn off switching of this diode. But before that, I just want to say that this T1 plus T2, it actually represents the forward switching on of the diode, or we can just call it as the forward recovery time, as it is called by many authors. So this is a forward recovery time which a diode needs to turn on. Now coming to the switching off characteristics of the diode, let us say that at the beginning of this interval T3, which I have just marked here, let us say the circuit conditions are now such that the diode is now about to start turning off. So you can see that the current falls, starts falling, and let us say that the current now, as the current is falling, let us denote this current by IR, and let us say that this slope therefore will be dir by dt. Again it will be determined by the elements of the external circuit in which this diode is placed. Okay. Now till the end of the T3, the diode current continues to fall and it actually comes to 0. But unfortunately the excess carriers which have actually got built up during the turn on, okay, they are still there and they are still not removed. So what happens, that the current continues to flow. So you can see that the current actually reverses here. After T3 the current has reversed, it is now negative, okay, and you can see that this is all because of this stored charge that we have seen here. And at a certain point we find that this current reaches its maximum, which we are denoting as the reverse recovery current IRR, and beyond that all the excess carriers are getting swept off because of the reverse current. Now there are hardly any excess carriers left. So the diode, it obviously cannot meet the demands of some external inductances which might be there in the circuit, and so it actually quickly falls to 0, marking the end of this recovery time. So I have just marked these intervals when the current became negative, okay, and after losing all the excess charge carriers it has quickly dropped to 0. I have just marked them by interval T4 and T5. Now typically this T4 plus T5, this interval is actually referred to as the reverse recovery time, and we denote this by TRR. And this triangle, of course I have to say that this is just an approximation, this will actually have a very, very complex waveform. So this we have just shown as a triangle because it is enough for our understanding and analysis. So this triangle, it actually, this area, it represents the extra charge that has got accumulated during the on condition of the diode, which has now been swept out, and the PN junction of the diode has regained its capability to block the reverse voltage. Okay. So basically now we are back into the condition where the junction can now block any reverse voltage applied to it, and hence we can actually reverse bias the diode. Okay. Now what I have written here is that how much is this charge, we can approximately write by just taking the area of this triangle and we can just say QRR is nothing but half into IRR, which is nothing, as we have seen, is the peak reverse current IRR into TRR, which is nothing but the base of this triangle. Okay. So, half into the peak current IRR into TRR, that will give me the area, which is nothing but the excess charge carrier that has been removed during the turn off process before the diode is ready to take the next condition. When the current is just falling during the interval T3, there is hardly any impact on the voltage. So, the diode, it continues to be in its normal on state because the current is still flowing, okay, and it continues like that. The junction of the diode is not yet reverse biased. In fact, the junctions must remain forward biased, so that there is a possibility for the excess carriers to be swept across, swept out. Okay. Now, at the end of interval T4, when the charge carriers have been swept off, the diode junction, it becomes reverse biased, and when it gets reverse biased, you can see that the voltage suddenly falls down. Okay. And again, because of the stray inductances, it shows some overshoot. We just call this peak value as VRR, and after that it just goes back and it just stays put at the reverse voltage that has been applied to the diode to reverse bias it. That completes this process of the switching off or turning off of the diode. So, this interval T4 plus T5, this is called the reverse recovery time, which is actually associated with the turning off of the diode. Now, the forward recovery time when the diode is turning on is not really a very critical thing, because we can see that this actually can take place very fast and it does not really have any delays as such associated with it. Okay. However, it is the reverse recovery time at when diode is getting turned off that we are more interested, because that is more critical, because unless the stored charges are actually removed or swept out, we cannot say that the diode has actually switched off, and it has a direct bearing on the speed at which the diode can actually work. Okay. So, what should be the frequency, what is the frequency at which my circuit is operating where I want to use a particular diode, which obviously be determined by this reverse recovery time that a diode actually exhibits, that we have just seen. Okay. So, T4 plus T5 is what we denoted as the reverse recovery time. Okay. Now, I can say that peak reverse recovery, if you look at the diagram that I have shown before, that the switching waveforms of the current and the voltage that I have shown before. So, if you look at the current waveform at the time of turn off, okay, you can actually see that the IRR value can actually be given by this term T4, that interval time duration, into the slope of the current at which the current was actually falling down. So, dir by dt, remember IR is what we decided to denote the falling current, the turning off diode current. Okay. So, let me just say that this equation is A. Okay. Now, we know that T4 is nothing but TRR minus T5, and I can then further, with some manipulation, I can say that this is nothing but TRR divided by S plus 1, where S is nothing but the ratio of the time T5 to T4. Okay. So, this is that ratio. Now, often we denote this T5 by T4, okay. The people who work with diodes, they call this as a snappiness factor. Snappiness factor, and usually T5 is much less than T4, and we say that such a diode is a snappy diode, okay, which can really turn off fast, that is what it is. But if you want to have this T5 to be comparable to T4, okay, then we got what are called non-snappy diodes, and these are also called soft recovery diodes. Now, one of the important things here is that we would like the current during T5 not to fall very suddenly in certain cases, because this might cause large voltage spikes to the other devices in the circuit. Okay, so if somebody really analyzes the circuit, as we will see later on in this course, we will see that a very small time t5, if the interval t5 is very small, we will find that the current would be so snappy, it will be so fast that the di by dt will be very high, and this will actually cause large voltages to appear across some other components and the devices in the circuit, which our circuit may not allow, and that is why we might have to go for what are called soft recovery diodes. Okay, now using this expression that we just got, if we just call this as B, this relation as B, okay, and we also know that QRR, the charge that got accumulated, which has to be actually removed during T4 plus T5 interval, is half IRR into TRR, and let me just call this as equation C. Now if I use the value of IRR from equation A, and if I substitute this into C, I can say QRR will actually turn out to be equal to DIR, the slope, into half of TRR square into S plus 1. This is the expression we will get, and let me just call this as D for our later reference. D can lead to this more comprehensive expression for the reverse recovery time. So TRR actually turns out to be the square root of 2 QRR into S plus 1, and the denominator of this expression within the square root is actually DIR by dt, and we just call this as expression E. Now if I use E in A, use basically this expression that we have just obtained E in expression A, then we can also get straight away IRR, the peak reverse recovery current. We can get this equal to 2 times QRR and into DIR by dt whole divided by S plus 1. The entire thing is the square root, and let us call this as equation F. Okay, now during the forward bias, when we were looking at the on time characteristics of the diode, okay, we find that when the current IF is flowing in the diode, obviously it has caused a lot of excess charge carriers to get accumulated in the device, mainly the drift region, the drift layer. Now let us say that this charge which has got accumulated is QF. Okay, let us say this is the charge. So this is the charge which has got accumulated during on operation of the diode. So this QF we can show is also equal to nothing but the forward current into tau, okay, where tau is nothing but the average lifetime of the carrier. So basically when a carrier is is there in a certain region, how long it can survive before it recombines either with a hole or with an electron. So this charge carrier, if it is a hole, how long it is before it recombines with an electron, or if it is an electron, how long it is before it actually recombines with the hole. So this average time is actually considered to be their lifetime, how much they can live in a particular region of a semiconductor. This is how it is defined as the most basic term. Okay. Now, so basically what we are trying to say is, if we know the lifetime tau and the forward current, we know how much charge has been accumulated in the device. Okay. Now some charge, when you are switching off the device, some of this charge QF, okay, so this QF actually has two parts. One of them is, let us say, QF1, okay, which is actually cleared off by recombination. Okay. But there is another component which is, as we have seen, the current actually reverses, okay, and that is what is clearing it. So, it is basically getting cleared by the reverse current. So, that let us call as the component number 2. So, clearly both QF1 or QF2 are smaller than QF individually. Therefore, from what I just discussed or I just explained, I can say therefore that the QRR which is swept out or swept away with a reverse current is less than QF. That is what we just concluded. Our QF2 part which I just explained is nothing but QRR in this case. So, that is less than this, and let us call this as an expression H. Now, once we know this, I can say TRR is less than, just using my expression E that we have obtained earlier, I can say TRR is less than 2 tau IF divided by dr by dt, and similarly we can say IRR is less than 2 tau IF into dir by dt. Okay, so, these are very nice and compact relations that we have got. Let us call them as star and double star, these two expressions. Now, this is an inequality, this is an expression which is an inequality expression, both of them. But in the worst case, I do not think that there is any confusion about this, that we can just replace these signs, less than signs or inequality sign by an equal to sign. There is another type of diode, not a silicon p-n junction diode, it is a different type of a diode which is used extensively in power electronic applications, and this is actually called the Schottky diode. Now, a Schottky diode is actually represented by this symbol. This is a Schottky diode symbol, and what it actually has is an interface of metal with semiconductor. Okay. Now, usually both N or P type semiconductors can be used, but in practice it is the N type semiconductor. Usually it is the N type semiconductor which is preferred for this. Okay. And the metal which is usually used for this application, for the Schottky application, it actually could be molybdenum or it could be tungsten, but they have their own advantages and disadvantages. Schottky diode is actually a majority carrier device. It is not a minority carrier device like the bipolar power diode that we have considered so far, a p-n junction that we have considered so far. It is actually a majority carrier device. Now, when we talk about a majority carrier device, that basically means that its mechanism is such that it does not really need to pile on or kind of accumulate the minority carriers onto the other side of the junction. Actually, the flow of the current in this case is constituted by electrons which are actually generated through thermionic emission. Okay. So, both metals and the semiconductor, they actually have this thermionic effect because of which the electrons are generated. One of the very big advantage of the Schottky diodes is that they actually incur very low forward voltage drop as the diode is conducting. Okay. The other advantage of course is that because there is no accumulation of minority carriers, there is no reverse recovery time problem here. So, these are really fast, they switch really fast. But the Schottky diode has a reverse leakage current that is much higher than the silicon p-n junction diode. I want to actually show you some typical data sheets. Now, for the power diodes, typically we would be interested in looking at some of these parameters. One of them is the junction operation temperature. So, the specification, what is the maximum junction junction temperature or junction operating temperature. So, what is the maximum temperature allowed as per the data sheet? This is a very important parameter for the design. Then what is the reverse recovery time, TRR? Then what is the repetitive peak reverse voltage? So, for example, in rectifiers, if you will see, you have these reverse voltages which are going to come across the device when it is reverse biased. Okay. So, what are these peak voltages which are repetitively coming and appearing across the device? This is again a very important parameter, and it is also important to see what is the one time maximum reverse voltage that will appear across the device. Okay. Then what is the peak forward surge current in the forward direction, what is the maximum surge current that is allowed, what is the average current which the device would allow, the diode will allow to flow, what is the RMS current that it will allow, what is the peak current that it will allow. So, all these are very important parameters that somebody will typically look at when looking at the data sheets of the power diodes. You can see there these parameters, you can see the forward average current, the forward RMS current, and you can see that for this example, which actually happens to be a 150 ampere stud type diode. Okay. You can see all these values are given. You can also see a very interesting thing here, which is saying I squared T at 50 or 60 hertz. So, what is that that unit, which is basically the kiloampere square seconds? What does it show? It basically means that we are trying to put a protective device, we are trying to put some protection for the diode. Now, I square T is given to you. So, some value is given to you, let us say we just call it value, and it is also given to you that how much time a certain current is allowed. Okay. So, you can actually get from here I square to be equal to value divided by T, and then you can just get the value of I by square root of this term. So, I is equal to square root of value over T. Okay. Now, this will give you basically this is the limit that is given by the data sheet. So, if your current is going above this, you must have a fuse in place that your device actually gets cut off from the supply, so that it is saved, otherwise you might end up destroying the device. We can also see on this slide, which is the second page of the data sheet of this particular diode, the maximum forward voltage drop, which actually is about 1.47, and you can see that all the other values are given at which this particular forward voltage drop will hold. So, it also gives a temperature of 25 degree centigrade. It says that what is the peak current, which is 600 amperes and so on. Under those operating conditions, it says that the voltage drop will be 1.47. And here there is a data sheet that is of a Schottky diode. Basically, they are calling it an ultra fast recovery time. So, basically you have the TRR to be extremely low in this diode. Schottky diodes, as I told you, are actually famous for being very fast with very low reverse recovery time, and you can see the maximum peak repetitive voltage and maximum working peak reverse voltage, which is about 200 volts for this particular device. Then you can see a forward current average, which is IF average is given. Then there is an RMS value of the current is given, which is allowed through this device. And on this sheet you can see what is the reverse recovery time, something that we really talked about so extensively some time back. So, it clearly says that this particular Schottky diode is having a TRR, reverse recovery time, of 70 nanoseconds when a forward current of 100 amperes is maintained, and there is a dIF by dt, the rate at which the current is varying is also given as some minus 200 amperes per microsecond. So, look at the really fast slope there. Okay. And the reverse voltage maximum is 133 volts, which is allowed, and even the temperature is given as 25 degree centigrade. So, under these conditions it is given that what would be the reverse recovery time of this device. And if you see the third row, it also gives the maximum reverse recovery current. the IRR value that we have involved in our analysis. Now based on the ongoing discussion that we are having about the speed at which the diodes can switch and about their maximum voltage capacities and so on, okay, it is customary to actually classify or categorize the diodes into 3 types. These are actually the general purpose diodes, which are typically used for rectifier applications, 50 hertz, 60 hertz rectifier applications. So here the speed of switching is not really important. So these diodes can be slow. The other type of the diode is what is called the fast recovery diodes. Okay, now these are the diodes which we want to switch fast, and therefore we expect their TRR to be very low or extremely low. Okay. These are the ones which are typically used for inverters and our DC to DC converters or chopper applications. And the third one are the Schottky diodes. They can switch very fast, as you know, their switching times are typically in nanoseconds, and they are used in switch mode power supplies. The problem is that because we are not able to go to high power with the Schottky diodes, they have certain limitations with the voltage, the maximum voltage that they can go to, they are not really available for use in other applications like inverters and choppers. Okay. So Schottky diodes, the third type, okay, I can just say that it is mostly the switch mode power supplies of the appropriate power levels where it is used. Now I will just write down some typical numbers here. Okay, so I can say that the TRR, if I just say this parameter and compare these 3. So for TRR I will say that the general purpose diodes would have something like 25 to something like 50 microseconds. The fast recovery diodes would have typically 5 microsecond of TRR, reverse recovery time, while the Schottky diodes would have in nanoseconds. So we just saw one Schottky diode which had something like 70 nanoseconds as a reverse recovery time. Okay. The other parameter, the important parameter that we know is the forward current, which can be carried by the diode, and for the general purpose rectifier the forward current rating typically is up to a few kiloamperes. That is really huge. Okay, thousands of amperes can carry. For fast recovery diodes typically it is less than 1 kA, 1000 amperes, typically less than that. That is also pretty large, but they are of course not having the same capacity as the general purpose diodes. Okay. And the Schottky diodes will typically have less than 300 amperes as their rating, allowed rating. Alright, about the rated voltage that these diodes, these 3 types of diodes can take, the rated voltage. The general purpose diodes typically 50 to 50 kV, 50 volts to 50 kilovolts. It's a huge voltage they can take. The fast recovery diodes can take something like 3 kV up to 3 kilovolt, and the Schottky diodes, as I said before, they are capable of only up to about 100 volts. Though there might be diodes which are now coming, Schottky diodes, where people are actually able to sustain higher voltages. With these words I end this session, and in the next one we will actually start with a new device, new power device, and we will see what other benefits we can reap from using those devices that will follow. Thank you very much for your attention.